All right, so I'm going to go over a certain few ideas in a linear algebra here. These have just clicked, so it's best to sort of capture them. So when we're trying to solve a set of linear equations, right? So when we are trying to solve a set of linear equations, we generally employ this particular equation, which is px equal to q, where p is a matrix that has all the coefficients of the linear variables. The x vector contains the variables itself, and then the q vector essentially contains all the constant values. So I just write one sort of simple quick representation very quickly. So a1x plus b1y plus c1z is equal to, let's say, d1. A2x plus b2y plus c2z is equal to, let's say, d2, and then let's say a3x plus b3y plus c3z is equal to d3, right? So generally the way we would write this would be a1, a2, a3, b1, b2, b3, c1, c2, c3 in a matrix, which is the p matrix. Then we'd have x, y, z vector as x equal to, the q would simply contain d1, d2, d3, right? This is generally how it sort of is, right? And then you would essentially go ahead and sort of solve this, right? Now the general sort of way to solve this would be using Gaussian elimination, right? So so the simple sort of idea is that you would essentially take this p matrix, let's call this q. You would make what is called the augmented matrix, muscle memory. So you would take the augmented matrix p bar q, which would then basically contain, you would have a1, b1, c1 bar here, and then d, a2, b2, c2 bar d2, a3, b3, c3 bar d3, right? This is the augmented matrix, and then generally you have like three sort of checks that you can perform, and then you would basically end up concluding whether or not you have sort of values, whether you can actually solve for this particular set of variables or not. That is essentially the idea, right? Now let's go a bit in depth here, because this depth is extremely important, because while we can in fact just look at certain few conditions and conclude whether this set of input will essentially have, this particular set of variables and equations essentially will have this particular solution or not, or where it will have that solution is more precise to say, right? But it's more important to understand what the sort of underlying idea is, right? So now let's look at these three columns that we have. These three columns are essentially what are called dimensions, right? So they are dimensions, or they are also called features as well. So if you have done some AI, ML, whatever stuff, you would have generally heard the word of features, right? Features generally sort of represents what parameters you have, right? That essentially that is called dimensions here. So you have three dimensions because you have three columns here. So generally what we say is the number of columns you would represent as n. So n essentially is the number of columns, right? So that is columns, right? Now here's what ends up happening here. So so what ends up happening is that you have the n as the number of columns. Now you would perform a sort of reduction to essentially bring it down to row echelon form or whatever, and essentially what you would check is, you would check two things. So you would bring in the rank of, let's say, p, and you would also check what is the rank of p bar q, the augmented matrix, right? And generally what we would do is we essentially end up checking what the values of these two are. So for example, if rank of p is equal to, or let's first go over the not equal to case. If it's not equal to rank of p bar q, then what we essentially end up saying is that, okay, there are no solutions here, right? Now generally we just gloss over why, but that is the idea here, that since the ranks are not equal, that there is no solution possible. Now then what you can also have is, let's say the ranks are actually equal, but the ranks in total are less than whatever the number of features is. So the ranks are equal, sure, but they are less than the number of columns. Now this would generally imply that you have infinite number of solutions, right? That is another one, but again we gloss over why that is the case. Another one is that both of the ranks are equal, but then also it is equal to the number of columns, it is equal to the number of features, it is equal to the number of dimensions, whatever you want to call it, and we say that there is only one solution here, right? That is how we write that, and that is how we say it, that there is only one particular solution possible here. So let's go over why that is particularly the case and sort of understand what's going on here. So essentially what is happening is, so let me just create a new page very quick. So what's happening here is, while we are clearly saying that okay, n is sort of the number of columns, right, what all of this really depends on is whether all of these expressions are, all of these equations instead are sort of linearly independent or not. That is basically what the rank is really trying to signify. So if you can essentially, let's say, have two columns, right, or whoops, I don't know why it's lagging, but yeah, essentially if you have, let's say, column 1 where you can write, let's say, 1 2 3, and let's say in column 2 you have written 2 2 4 and 6. Now these two are linearly dependent, because the idea is that once you have C1, C2 doesn't really give you any new information. It is completely a waste of space and it provides no new information. So essentially C2 can simply be written as 2 times C1, and therefore it provides no real value. Now if you consider C3, for example, where it could just be 5, 7 and 9, so here clearly C1 and C3, like if you try to obtain C3 from C1, it's not going to happen in terms of a sort of a, a scalar product. It's not really possible. Even if you try it with C2, you won't really get it, right? So they are linearly independent. So if you were to try to essentially make like a particular matrix through this kind of a situation here, what would end up happening is, while sure you may have n equal to 3, your rank may actually end up being 2. Right, that is basically the idea, because what's happening is that there's only two linearly independent expressions that, or set of features that you have, and the third one is redundant, right? So that is basically what happens, right? And there's a very interesting sort of a theorem that comes up, which is also very important, which is the rank nullity theorem, which simply states that provided that you have number of let's say n is the number of columns that you have, the total number of, or rather the let's just say this, that given the number of columns that, or the number of dimensions that you have is n, it is the sum of the row rank and the nullity. Right, now what is the nullity? So nullity simply refers to the situation where both of these columns or any number of columns are essentially linearly dependent, right? So here in this case, as we sort of notice, C1, C2, right, they are linearly dependent. If you have one, you can find the other. Now that basically means that the nullity of this particular set of this particular system is essentially 1, right? And this now brings me to the next idea that is very important to sort of bring up here, that we have, whenever we have any sort of a matrix, like even let's look at the P matrix, it basically have two spaces. It has the row space and then it has the null space, right? So the idea of the row space is that whatever value, like whatever vectors that you have, they will never equate to 0. Or I'll explain this better, but essentially that is the idea, that these can never essentially give you the value of 0, but then whatever vectors you get in the null space, they will always equal 0. That's it. So given a particular space, you can subdivide it into row space and null space, where row space will basically be a set of vectors that can never provide you 0. They will only provide some distinct non-trivial values, whereas null space will essentially provide you a trivial 0. That's it. So now how does that even make sense? So the idea is, let's say if you have something like this, let's say 1 2 4, let's call this 6, and then let's call this 5 7 8, something like that. So essentially here's what happens, right? So if you look at row 1, row 2 and row 3, you will very clearly notice that row 1 is or rather row 2 is equal to 2 times row 1, which means that these two are linearly dependent, right? They're linearly dependent, and what you would end up having is that you can essentially eliminate. So if you were to try to get the row echelon form of this, you would essentially end up with only, let me not write it like this, you would only essentially end up with R1 and R3 as the non-zero rows, whereas R2 would simply get completely eliminated, right? So if you were to write the row echelon form, you'll basically end up finding that the rank of this particular thing is 2. That means if you ever use these two vectors and multiply with any sort of another vector, right? Or rather, okay, let me be very specific here. So if you take this particular matrix and you multiply it with a particular vector, right, and if you are using the row space vector specifically inside the P matrix, whatever values you will get will not be 0. They will never be equal to 0, whatever you get here, right? But then if you consider the null space vector, basically this particular 2 4 6 guy, This basically is a particular case where any you can essentially get any zero here, or I guess that's not a very proper way to say it, but essentially it leads to zero. All roads through this particular basis vector would be to zero only, right? So, and also since I mentioned the word of basis, so the idea is that since we have R1 here, and since we also have R2, so you have 1, 2 and 3, and you have, let's say, 5, 7 and 8. The idea is using these two vectors, these two essentially end up acting as the basis vector. So the point is that to reach any space that is within this particular P matrix, you only really need these two vectors, and you can get to any vector or using these two things. So I mean, it's just like how we have the coordinate system where you can write, let's say, 1, 0 and then 0, 1, right, as like two vectors. So this would be the x vector, this would be the y vector respectively. And then if you want to reach, let's say, 3, 4, a point in xy plane, you would simply write 3 of 1, 0 plus 4 of 0, 1, and that's how you would essentially end up at 3, 4. That is basically what is happening with this as well. It's the same thing. And then when you consider row 2, which is so now back to the original P matrix that we had, where we notice that 2, 4, 6 is sort of the linearly dependent guy. This guy is basically what is the null space basis vector, right? So that is what it is. So no matter what value you give to this particular null space basis vector, anything that you give it, it'll reduce it to zero, it'll consume it, right? That particular dimension will not be used. Now the idea is that whenever you are having expressions like, so let me just write this because I noticed this. So if you have px equal to q, right, and if let's say q is equal to some q is not equal to 0, let's say q is not equal to 0, in this particular case, of course, the idea is that this particular point q exists in the row space, right? So it's non-zero, right? So of course you'll have to, so the non-zero sort of what is it called, the sort of non-zero part of P is essentially going to be used, or the row space within P is going to be used to essentially reach Q, because it is a non-zero point, or non-zero vector rather. Now if provided that q is 0, like if we assume q is 0, then the only way to reach it is going to be through the null space, right? That is the basic idea here, which is extremely important. So whenever we have any sort of expression where we are writing px equal to 0, the point there is that you won't really reach there through the row space vectors. No, you will reach there through the null space vectors, right? That is sort of the basic idea, right? That was extremely important, that I sort of just stumbled across while solving some problems and such. Now also one very interesting idea is, because of this whole idea that we just have here, row space and null space, I also want to sort of qualitatively go over what it really means for the rank to be less than the number of features, right? And for there to be infinite solutions. So the idea is as follows. So let us say you have like let's say total of, let's write it like this instead. So let's say you have 100 total columns, right? So you have 100 total columns. Now the idea is that basically what you're doing is, whenever you're finding a rank, is you're finding out how many of these 100 columns are essentially linearly dependent, right? So you're trying to eliminate the linearly dependent guys, so that you only end up with the linearly independent set of vectors, so that you can get that basis and then use it to find the non-zero solutions. So essentially you can think of it like this. If you end up with a split like this, right? So let me write it like this. So you have 100 and you end up with a split like this, where you have, let's say 98 dependent vectors and only 2 independent vectors. What that means now, if you really think about it, is that whatever output you're going for, so let me write this expression. So px equal to q. So let us say P is the matrix for which I'm claiming that it has, let's say 100 columns, right, which would mean 100 dimensions. So let us say what this would mean is, if 98 columns are essentially linearly dependent and 2 are linearly independent, the idea here would be that 98 columns that we have here are essentially these 98 dimensions are completely useless to reaching a particular point. It does not matter. And generally what this would also mean is that Q is of 2 dimensions, right? That is sort of the important idea here, that even though you may have 100 dimensions, you only really need 2 dimensions to essentially reach Q. Now the way I can sort of explain this, which really stuck with me, because I had like a sort of a flash and I realized this, right? So okay, I drew the arrow in the wrong direction, so let's draw this, right? So I'm pretty sure this diagram is very common, XYZ plane, right? So very nice and simple. Now assume that, let's say, P is in fact a vector. Let's just consider it that it is a vector. It can have one column, who cares, right? So let us say we are at a, like, let's say 1 2 3. Just consider this argument, right? It will make sense. Let us say I'm at this particular point. Let's say so don't call it P, rather call it X. Let's say I am at an input point of X, 1 2 3, right? I'm at 1 2 3 in the XYZ plane. Now what I am trying to do in Q, so I am trying to essentially reach 0. That's it. I'm not trying to reach, now technically you would write it properly as 0 0 0, but assume that I only want to reach 0 essentially, right? I'm not specifying in like 200 dimensions or 3 or whatever. I'm just trying to reach the 0 that is in the that is in one dimension. Now the way you could do it, if you think about it, is in 3 ways, right? So you could either have 0, so you could essentially take 1 2 3, you could rip off 2 3, so you could drop the y and z terms, and you could take the x and you could make it a 0. You could also do 1 2 3, destroy the x and the z, and then basically reach 0 through y. You could also take 1 2 3, you could drop the x and y terms and essentially reach 0 through z. So if you really think about it, what that means is that to reach this particular one dimension, which is a lower dimensional point, what has to happen is that you have to select one of these sort of vectors, one of these particular dimensions that you have within the x input vector through P. Okay, through P, you can think of it like this. P is a transformation machine. X is whatever the input is. So yeah, this is another sort of thing. Of course, I'm sort of jumping around, but the idea is, so if I'm writing Px equal to Q, now X is in fact whatever the input is, right? Now Q is whatever the output is, and both of these are vectors, right? That is how we generally look at them. Both of these are vectors, whereas P is essentially a machine that chooses which of the row space, which of the dimensions are to be used to reach the particular output through the input. So P is the one that is choosing which dimensions to use from X to essentially reach Q, right? That is basically what is happening. Now another very interesting way to sort of go about it is, if you think about it, so for example, consider PCA, right? Principal Component Analysis. It's just a fun parallel or not a parallel, it's just a fun application that I realized how it actually works, which is kind of funny. But so the idea is, let's say you have like a particular whatever data set or anything which is of 100 dimensions. Now 100 dimensions is not very good to use, so you would generally want it to be somewhere in like 2 to 3 dimensions. 2 is sort of the standard. So the idea is that this is your input, the 100 dimensional whatever input you have, right, is basically whatever your input X is, and what you want is the 2 dimensional thing, and that is therefore the Q. So what is happening is, so let me write, so X will in fact essentially be your 100 cross 1 vector. Q will then be, what will it be? It will be a 2 cross 1 vector. So now if you think about it, what should the dimension of Q be? So clearly the second term has to be 100, right? And here you would have a 2. So P on its own, the P matrix that we have should be a 2 cross 100 matrix that will basically consume the X vector, or basically process the X vector and transform it into Q, right? And now if you think about it, what has to happen is, now since we are specifying in this P matrix that okay, or we are not even specifying, think of it like this. Now since the dimensions that we need in Q are only 2, what this means is that only so sort of essentially the rank is 2 and the nullity is 98. Now therefore what actually can happen is there can essentially be 98 different variations of P, because the P is the machine that sort of defines which of these 100 columns that you have, or which of these 100 row entries that you have, because of course we are writing it as columns, but we'll take the transpose and write it as a row. But the idea is that it will essentially select which of the 2 columns to essentially select to perform the translation or the transformation. So the idea is, let's say if you use P1x equal to Q, Because of this particular p1x, what could happen is, let's say row 1 and row 2 are the ones that are selected to perform this particular transformation. The rest of the rows from 3 to, let's say 100, since we started counting from 1, all of these rows will essentially collapse to a 0. They will be consumed completely. Now of course, because of this there will be some approximation error and all that. We don't care though, that is completely fine. The point is that you're able to come to a lower dimension space from like whatever your 100 dimension was. Let's say now you choose another combination or another matrix P2 such that it is essentially selecting only R2 and R3, right? And you're reaching Q. Now what this would mean now is that R1 and basically R4 to R100 are all collapsing to 0. So basically what is happening, whenever these guys are collapsing to 0, the null space is essentially the one that is sort of consuming them, or rather they are the ones that are in the null space, right? That is basically what is happening here. So that was sort of the basic idea that I kind of understood while sort of trying to look beyond only the formula, and these are the things that I kind of captured while understanding it. So I thought it's pretty decent to just go over, and that was about it. So yeah,